I'd like to thank you for listening in on our discussion today on detention planning, specifically using LiDAR for value-added flood damage reduction analysis with relation to planning where you can build detention facilities in the landscape. My name is Zach Hermann. I'm a professional engineer working for Houston Engineering out of our Fargo, North Dakota office. I've done a lot of this detention planning effort scale within the Red River Basin on the Minnesota side, as well as over on the North Dakota side of the Red River. So the first topic we're going to talk about is just an example application within the Buffalo Red River Watershed District in northwestern Minnesota, right around the Moorhead area. The project we're going to be discussing is the Upper South Branch Water Resources Management Plan. Basically what this project consisted of was the project mediation team coming up with a series of solutions for a multitude of complex problems that exist within this particular watershed. Things such as sedimentation of channels from the agricultural fields within the project area, causing reduced channel capacity, which leads to flooding in certain regions, breakout flows, impairments to water quality, also related to agricultural runoff within the watershed. A multitude of options have been analyzed to date. One option has been setback levees that control the breakouts that currently exist. What we're going to be talking about today, the flood water retention and wetland restoration components of the project, and also installation of better management practices across the landscape. So if we look here, we can see the project watershed with the LiDAR color banded behind it. So the whites that you see correlate to high elevations, and as you work your way to the west, you get to where you have more of a bluish teal color down towards the, well, I should say up towards the northwest portion of the watershed. That correlates to lower elevations. So as you can see, in general, we have a trend of higher elevations in the east working our way down into the lake plain to the west. Now, with the aid of the LiDAR, we're able to derive what the project watershed looks like, which is the purple boundary that you see. The non-contributing areas, which are the red hatched areas that you see on the map, as well as the hydrography of the particular watershed as based on the LiDAR information, which are the blue lines that you see on the map in front of you. We know in the particular watershed that one of our problem areas that exists is this reach where my mouse is. So with the hydro DEM, or the DEM that we've applied the reconditioning to, we can derive what the subbasin is from our problem watershed. The problem we know exists there is that, well, it's actually a multitude of problems. This is where our breakout location is. This is where we have sedimentation occurring within the channel. And this is also where we see some of the most significant flooding of agricultural lands adjacent to the channel itself. So basically, if we have our project watershed, we know where the runoff is coming from. So then we can start looking for sites in the landscape where we could possibly slow the water down a little bit and not have all those erosion and sedimentation issues that occur as a result of the water coming so fast off of the upper portions of this watershed. So if we zoom in and take a look at this watershed, it's very typical of a lot of areas within the Red River Basin. You know, we've got a lot of potholes and really deep incised depressional areas in the eastern portion of the watershed, lakes, sloughs, those types of things. As we move further to the west, we reach the what's referred to as the beach ridge, or an area of steeper slope. This would basically be correlate to the bank of the old Lake Agassiz that used to be here. And as we continue on down towards the west, we get into flatter and flatter topography, which would be the lake bed or the bottom of old Lake Agassiz. So when we're looking to place retention, we know we want to put it someplace where we have sufficient fall, where, well, when I say fall, we have sufficient slope on the landscape where we can back up a reasonable amount of water with a reasonable embankment height. If we have too much slope, we need fairly unreasonable embankment heights to be able to get a high enough volume to make a meaningful difference. If we get into flat topography, embankments get to be very, a very low embankment height will back water up for for a very long distance. So there's kind of a preferred region, which is kind of at the base of that beach ridge I was talking about to place retention sites. Now, as you can see here, this is one location that we had identified. The green dashed line correlates to a potential embankment alignment that we had identified. It's trying to use this existing escarpment that you see right here, and also backwater up in this particular region at this location. So when we take a look at that with the hydro DEM again, we can derive real quickly what the project watershed would look like, or what the area would be that would feed this particular retention location, which you see highlighted here in the yellow line. Now if we zoom in on that location with the LiDAR, we get a really good sense of what the drainage characteristics are within the site itself, what the topography looks like. That really helps us out in figuring out how are we gonna, once we start draining the site after the flood, what type of alterations are we going to have to make to the landscape to make sure the site drains back to the existing conditions. It also, by having high resolution ground elevation information within the site, we can quickly derive what the elevation storage curve would look like, or at each elevation within the retention location. We know what the corresponding volume available is, as well as the surface footprint. You can see that illustrated here. Each color on the map correlates to a different elevation, and the curve down in the bottom there, each elevation has an associated acre feet of storage associated with it. Now, once we've had the site identified, the next step is to really quantify what is the benefit to our project area. Now, to do this, we had a hydrologic model, a HEC HMS model for the area, as well as a HEC RAS hydraulic river routing model that was developed for the region. So we could basically analyze what the benefit was within the project area itself by implementing detention at different locations. So what you see here, this was again with the help of the hydro DEM, we were able to derive what the travel time characteristics are for this particular site, as well as points downstream. Once we know that, we can begin routing flood hydrographs into the site and what the corresponding outflow flood hydrograph would look like as a result of implementing that site. And by comparing existing and proposed conditions, you can see here hydrographs from a couple HEC RAS model runs, where just as you'd expect with detention sites, the closer you are to the site, the most benefit you see, which you see in the bottom hydrograph, substantial reduction off the peak, as well as substantial volume reductions. And as you move downstream and you accumulate more area, so that basically the percent of area you're controlling is constantly reducing as you move downstream, you see less benefit as you move further downstream, which is illustrated in the top hydrograph, where we are still taking volume off of the peak, but it's substantially less percent volume out of the existing versus the proposed hydrograph at that location. And the LiDAR also, this isn't necessarily with the hydro DEM, but the LiDAR itself really does help us out when it comes to establishing things like preliminary design of these structures, figuring out how much embankment we would need to build it, for example. Taking a look at, after we do our sizing of the structure for the spillway, is determining what our estimated easement requirements would be based on inundation areas, things of that nature. And that's illustrated here on the slide that you're looking at, where you have the gated the gated storage flood pool, as well as the emergency spillway flood pool. If you have any questions, again, my name is Zach Hermann. I work with Houston Engineering out of our Fargo office, and my email is on the screen. So if you have any questions, just feel free to let me know.